Looking into space. That is the signal from an American space probe as it was heading out past the moon to become a satellite of the sun. It's from interpreting such coded signals as these that most of our information about space is built up. The first of this series of 5 programs is a general survey of the whole subject, looking into space, and is introduced by John Stobbs.
New rockets, new space probes and new satellites are becoming almost a commonplace. In fact, we take them for granted. At this moment, 9 satellites are circling the Earth and others the Sun, each one put there to answer some specific scientific question. They were all sent up by Russia or America. But we in Britain could put up satellites too within the next 5 or 6 years, simply by developing the military rockets which we already have. This is something Parliament has to make up its mind about, but we do know that it would cost only a fraction of what America or Russia is spending. Well, why is the whole subject so important? As an ordinary journalist with no scientific training, I've been talking to a number of the leading scientists already engaged in it. And during these 5 programs, some of them are coming along to put us in the picture. Opposite me now is Professor Sir Harry Massey, Chairman of the Royal Society's Committee on Space Research. Sir Harry, what does space research really consist of?
Well, for scientists, space research has a quite definite meaning. It's research made possible by the availability of powerful rocket motors to take instruments into the high atmosphere and beyond, far above the 20-mile limit, which is the limit reached by balloons. Such instruments can make observations of the outer regions of the atmosphere and of the universe around, which were formerly beyond our reach. By exploiting these extremely powerful new techniques, the old sciences of astronomy and of geophysics, the study of the Earth, can be greatly extended, while there is the prospect of building up new sciences of lunar physics, Martian physics, and so on. It is because of these prospects that scientists are very interested in space research. For them, the aim is the attainment of deeper insight into the mechanism of nature. It is this enlightened curiosity which draws them on. They have no goal in the shape of some application to industry or health. We must remember, though, that the results obtained by scientific research, carried out for its own sake, have a way of leading to unexpected new applications. A striking example of this is the case of nuclear physics. In 1937, Lord Rutherford, who practically initiated nuclear physics, himself stated at a meeting of the British Association that he could imagine no foreseeable application. By 1945, only 8 years later, atomic energy was released on a grand scale by man. A vast new power had been set to work. And so it may be ultimately with the results of space research. There is, of course, one very closely related matter which is in many people's minds today: travel in space by man himself. The question here is this: is space travel an end in itself, or is it another way of conducting space research? Viewed as an instrument for space research, man is said to be more flexible than automatic instruments. But this may not apply in the space environment, where his continued existence must depend on the satisfactory and automatic working of a great complex of instruments. However, in any case, it seems obvious that man's appetite for exploration will compel him into space, and much research by instruments must pave the way. Space travel can only be justified for its own sake, not purely as a means for carrying out scientific research. We shall not attempt in this program to argue the pros and cons, but concentrate mainly on the scientific pursuits of space research, which should prove to be exciting enough. In the 4th program, though, I believe something is going to be said about man in space. Why should there be all this scientific interest in studying the high atmosphere and the even emptier space around the Earth? Isn't it a matter of trying to find out more and more about less and less? That's quite incorrect. Even some functions vital to life on Earth are performed by the upper atmosphere, extending well above the 20-mile limit reached by balloons. For example, meteors of any size are burned up or evaporated before penetrating within 50 miles of the ground, while certain ultraviolet rays from the sun which would kill off all plant life if they reached the surface, are absorbed a little above the balloon limit by the presence of a tenuous layer of ozone. Radio, telephone and broadcast communications over the whole Earth are only possible because of the existence of the ionosphere. This is a region of the atmosphere which extends upwards from a height of about 60 miles to several hundred miles. It contains a concentration of free electrically charged atomic particles, sufficient to reflect back the radio waves, which would otherwise pass out from the transmitter directly along straight lines into space. Apart from these properties of the high atmosphere, which are of direct importance to man, there are many others of great scientific interest. There is the magnificent polar aurora, which glows in the sky in high northerly and southerly latitudes at irregular intervals. This happens in association with the appearance of spots on the sun, strong disturbances of the compass needle known as magnetic storms, and interference with long-range transmission of radio waves because of disturbances in the ionosphere. The auroral displays are produced mainly at heights of 60 miles or more in the atmosphere. All of these interesting aspects of the high atmosphere were studied for many years before space research became possible. But there are some observations of key importance which cannot be made if one's instruments are all on the ground. Perhaps the most vital of all is the knowledge of the radiation from the sun. These radiations include a very wide range of wavelengths, extending from the shortest gamma rays, which are essentially radio waves of less than 1/1000th of a meter wavelength, through X-rays 100 to 1,000 times longer, ultraviolet rays, visible light, infrared rays, to the radio waves we receive on our wireless sets and beyond. Of all this range of billions to one, the only waves which penetrate through to the surface are those comprised in visible light, waves between 30 and 50 millionths of a meter long, and those in a narrow band of radio waves of length between 100th of a meter and a meter. All the rest are absorbed in the atmosphere, including particularly those which are shorter than visible light, such as ultraviolet and X-rays. These do not penetrate to within 50 miles of the surface. Yet it is these very radiations from the sun which are primarily responsible for so much of the behavior of the high atmosphere, including the ionosphere. Because they do not reach to the surface, they cannot be studied from the ground. We must send suitable recording instruments above the absorbing atmosphere to measure their intensity. Without this information, we cannot understand how the sun produces the atmospheric effects in which we are interested. This applies also to those streams of charged particles which the sun pours out into the space around it at certain times, usually when it is spotty. These streams are in some way responsible for the auroral displays and the associated phenomena. They also maintain relatively high concentrations of charged particles, or particle radiation, in the space around the Earth where its magnetic field is effective. These radiation belts are of considerable importance for space travelers, as exposure to too high an intensity of the radiations would be dangerous to life. Once again, we can only study these particle radiations and their effects by means of instruments transported out to thousands of miles from the Earth. Just as the atmosphere blocks off the sun's ultraviolet and X-rays from us at the surface, it prevents us from receiving any such rays from other parts of the universe, from the stars, nebulae, and interstellar space. Without space research, we are confined to viewing the universe in visible light and a narrow range of short radio waves only. We now have the prospect of new branches of astronomy in which the viewing instruments are outside the atmosphere, and we can examine the universe in radiations of all colors, all wavelengths, instead of the few that reach us on the ground. There is, of course, one of the most interesting questions of all which will be answered in the foreseeable future. Is there anything which could be called life on our neighboring planets, Mars and Venus? Before very long, it should be practicable to begin the search for living organisms, or their products, by automatic examination of samples scooped from the surfaces of Mars and Venus. It's not possible to do more than speculate on what may be found. Apart altogether from the biological examination of our nearest neighbors in space, They offer a vast field for study simply from the point of view of their physical properties. This is interesting not only for its own sake, but because it throws light on the nature and history of our own Earth. Thus the absence of any appreciable lunar magnetism, indicated from the observations made from the Russian vehicle which hit the moon, supports the present most generally accepted theory of the origin of the Earth's magnetism. Most of the members of the solar system belong to one family, which have not gathered together fortuitously, but are all related. Further knowledge of one helps us to understand the properties of the others. There are many other sides to space research. It can throw light on the nature of the cosmic rays, extremely energetic particles which reach us from all directions, but whose origin is unknown to us, and on the nature of gravitation, the weakest of all known types of force. Once outside the atmosphere, we may look inwards to garner information on a worldwide basis about atmospheric motions and about the loss of heat from the Earth. We can even obtain new information about the shape and structure of the solid Earth itself. There's abundant material to study if we can send suitable instruments to the measuring places, high into the Earth's atmosphere and beyond to the moon and planets. But how can this be done, and what technical developments are required? First of all, it is necessary to use rocket propulsion, independent of the existence of any external oxygen. The rocket motors must be powerful enough to propel vehicles weighing 100 pounds or more out to very great distances from the Earth. It's also necessary that the vehicle be guided at the appropriate speed into the path which it is to follow, and that it be tracked as it pursues this path, so that its position at any time can be determined accurately. The scientific instruments within the vehicle must function correctly under unusual environmental conditions, involving high shocks, vibration, and low external temperature. Observations which the instruments make must be transmitted back to stations on the ground in the form of coded radio signals, as the vehicles are usually not recoverable after launching. In Britain, the Royal Aircraft Establishment has been closely concerned with these developments, and Mr. Cornford of that establishment will tell you something about it.
The first requirement, of course, is a rocket engine of many tens, if not hundreds of tons of thrust. Such engines are also necessary for the propulsion of intercontinental ballistic missiles, and the propulsive needs for space exploration are generally available as a byproduct of military developments. The great majority of satellite and space probe launchings made so far have in fact used military rocket engines. The first of these high-thrust engines was developed in Germany during the last war to power the V-2. This produced a thrust of about 35 tons and accelerated the V-2 to a speed of roughly 3,500 miles per hour. Well, let's see how this performance compares with the needs of space investigations. For these, there are two important speeds. The first is the speed which must be attained to put a body into a circular orbit at an altitude of 100 miles or so above the Earth. This is about 17,500 miles per hour, and is only about 2,000 miles per hour more than is required to project a 5,000-mile range ballistic missile. The second speed, which must be exceeded for interplanetary flight, is that required to escape from the dominance of the Earth's gravity into the field of attraction of the Sun. Near the Earth, this is a little above 25,000 miles per hour. A body projected with such a speed would leave the Earth forever and become a satellite of the Sun like the Earth and the other planets. Now, what sort of rocket thrusts are needed to achieve these speeds? In the current state of rocket technology, the ratio of the weight of the whole rocket to the weight of the satellite which it can put into a circular orbit near the Earth is about 80 or 100 to 1, and the corresponding ratio for escape is nearer 1,000 to 1. If we want to put a satellite weighing a ton into a near-Earth orbit, the weight of the launching rocket will be nearly 100 tons, and in order to get this safely on its way, it would need a launching thrust of between 130 and 150 tons. Similarly, the 800-pound Russian Lunik 3, which photographed the moon, must have been launched with a thrust of 300 or 400 tons. What advances since the days of the V-2 have made these things possible? There has been a general scaling up in size of rocket engines, and smaller engines have been coupled together to give the large thrusts required, but the ability to accelerate to very much higher speeds can only come from savings in the useless or dead weight which the rocket thrust must accelerate, as well as the useful satellite payload. This dead weight includes the engines themselves, the propellant tanks, and the equipment to guide and control the rockets. Improved materials and methods of lightweight construction of tanks and engines and miniaturization of electronic components have allowed tremendous savings to be made. And in a large modern rocket, the dead weight need only amount to 6 or 7% of the total, all the rest being fuel. But even this is not good enough for Earth satellites and space exploration, and use has to be made of rocket staging. 2 or 3 separate rockets or stages are mounted one on top of the other. The first stage rocket is fired, and when it runs out of fuel, its dead weight drops off in mid-flight, and the second stage then starts off, adding its own speed to that already given to it by the first, and so on. All the satellites so far launched have had to use this technique.
Well, thank you very much. We'll be hearing more about rockets and their guidance next week from some of your team at Farnborough. So, Harry, I believe you had something more.
Yes. We haven't mentioned really long-distance tracking. For example, radio signals conveying information from the American Deep Space Probe, which passed the Moon and became an artificial planet, were received out to distances of no less than 400,000 miles. Finally, as we learn more and more about nature, we gradually become able to modify it. And there's one very exciting example of that. The Americans have carried out 3 experiments involving the temporary and observable modification of the properties of regions of space greater in size than that of the Earth. 25 years ago, it would have been thought impossible to send instruments to make observations in space. How much more unbelievable would it have seemed to be able to modify the properties of vast regions of space in a controllable and accurate way? This has been done, as you will hear in a later program.
Yes, for laymen it's astounding, of course, and almost frightening in its implications. Logically, we ought to be working on this whole business as one world, not in expensive international competition. Well, one of the more encouraging things at present is that we do seem to be moving in that direction, and here is Mr. M.O. Robbins, who is United Kingdom delegate to the scientists' own International Space Research Committee, to tell us something about that. What's going on, Mr. Robbins?
Well, here are a few examples of what's going on. This month I shall be going to America with a small team of scientists to meet our opposite numbers there and sort out the details for the launching of some of our space research instruments in one of their satellites. This all came out of an American offer made at The Hague last year to scientists from the member countries of the International Committee on Space Research, COSPAR. Several other countries are considering taking up the offer, but we have gone further and have 6 experiments which have been judged both by the Americans and by scientists of COSPAR as well worth putting into orbit. Then the Americans are planning to have some of their instruments flown in the British Skylark research rocket in Australia. And both Americans and Russians are grateful for British Commonwealth tracking observations, for instance by the Jodrell Bank radio telescope, on their satellites and space probes. This, of course, is only one part of the whole international scientific picture. Scientists are rather like cricketers. They're enthusiasts. Give them a chance to talk, and common scientific interests very soon override national barriers. It's a fairly safe assumption that, say, Van Allen of America and Vernov of Russia are in pretty close contact in their studies of cosmic rays. This is nothing new in science, of course. It is just that those of us who are interested particularly in space research in different countries are naturally getting together. But it's not all quite so simple as that. Let me put things in proportion a little more. First, we have this International Space Research Committee called COSPAR. This, in essence, is non-governmental and deals with scientific research carried out in space rather than with rocket engineering. It is based on the international scientific unions and national scientific academies of various countries. Already, the organization of working groups of scientists is well underway, considering joint experiments, how best to handle and disseminate data, and so on. It has arranged 3 world data centers for space research, one in Moscow, one in Washington, and one not far from London at Slough. These centres have an important job to do, if only in overcoming the mere obstacles of language and the different publishing habits in various countries. The Russians, for instance, tend to publish brand new research results on the front page of Pravda, the last place a Western scientist would have thought of looking for them. All this sort of thing will undoubtedly go ahead quite happily and effectively, barring any major international disturbances. There are, however, some very real practical limits to actual cooperation in experimental work which must be mentioned. Scientifically, it may not matter much whose rocket puts one's instruments into space, but anyone who has worked in this field knows how very much easier it is and how valuable the engineering and technical experience is if the do-it-all-yourself approach is possible. Again, analysis of the very large amount of data coming from satellites might be spread over a number of small countries, thus using the brains of those who can't afford a full space program. But there are limitations here. A great deal of scientific advance comes from research teams noticing some slight deviation in results from those expected. Any sort of sausage machine treatment of data by teams without the first-hand contact with the experiment might easily go straight past the vital information. We must realize, though, that the more ambitious space research becomes, the stronger the case for complete international cooperation. Speaking purely as a scientist, that seems to me to be the only rational way to tackle the really big things. But perhaps human nature is not yet quite as rational as this. On any grand scale, space research and the necessary techniques of launching, tracking, and communication will tax the knowledge and skill of the whole world, let alone the demands on manpower and finance. While we seem to be moving in the right direction in international cooperation, we can perhaps learn from experience how a little more advanced knowledge of plans can give us a lot more value from some experiments. For instance, if the release of the sodium vapor cloud from the Russian Lunik 2 had been more widely known earlier, many more valuable observations on it might have been made. This illustrates a difficulty about giving advance notice of launchings. The Russian tendency is to announce a launching when it has successfully happened, and this may lose valuable observation time. On the other hand, the Americans, with their different ideas on publicity, must sometimes place the unfortunate scientists and engineers in an embarrassing amount of limelight when things go wrong. Meanwhile, we have just held the first International Space Science Symposium at Nice. About 100 scientific papers were read, mostly by the Americans, but a dozen or so each from Russia and Britain, and a few from other countries as well. The whole thing was very friendly and stimulating, not least because of the many informal talks amongst the scientists of 20 nations. This seems to us all to be a good start.
Thank you very much. I see that Professor Lovell of Jodrell Bank has been making the most emphatic plea that in the race to get to Mars, nothing shall be done which might even conceivably affect any possible form of life there. How important do you think that is, Professor?
Oh, I think this is very important. There are two sides to it. The one thing you don't want to do is to discover life on Mars, which is very similar to that on Earth, and find that in fact it had all come from the Earth in the first space vehicles. So you have to make very sure that your vehicles are well sterilized. This is a very difficult thing to do. But there's a second important side of it also, and that is that any living material, or in fact any chemical products of living things on the Earth, which are carried, say, to Mars, might very well influence disastrously any life which is there. It may kill it all off, just as, the South Sea Islanders suffered very badly from the various diseases which we brought over there in the days of exploration.
This is something that is being looked at by the international committees, isn't it?
Yes, there's an international body set up to consider this, and they have reported very strongly on what is desirable, and have initiated work to try to improve methods of sterilizing vehicles.
What do you personally feel about the prospects of finding some sort of vegetable life on other planets?
Well, I think that on Mars there's a very good prospect that we'll find some form of vegetable life, something like a moss or something of that sort. But one of the important aspects of it all, I think, is not so much just this question, but whether there can be any other kind of life than that which is developed on the Earth, based on different chemicals. We don't know whether this is possible or not, and it would be very interesting to know the answer to this question.
Cornford, what about the projection power of rockets? Are there any new steps you can foresee that may come?
Oh, there are published plans in the United States for rockets of very much greater thrust than any I've spoken of. Million-pound thrust, 500-ton thrust rockets, and even larger than that. And of course, one of these days we hope to be able to use nuclear propulsion for rockets. This will be a very complicated and a very difficult subject, but it does give a tremendous payoff if nuclear engines can be used to drive rockets.
There's another thing that comes up in this. Satellites depend on gravity for keeping them in orbit. Yet I gather there's some sort of mystery about gravity. Professor, what exactly is gravity? Can you tell us?
I wish I knew the answer. We know less about gravity than the three other types of force which we know exist in the universe. Gravity is by far the weakest of all the forces, and we have to investigate it in a grand scale.
What are those three main forces?
Well, the strongest of them all is the one which holds the constituents of the atomic nucleus together. It's the force which does work for us in atomic energy plants. The second one is the force which takes place between electric charges and between magnetized bodies. And then the third one, which is very much weaker still, is the one which produces certain radioactive phenomena. And those are the only three we know of apart from gravity at the present time. It's quite likely that space research will help us to understand the nature of gravity in the future.
How could it do that?
Well, it would provide us with many more large bodies to experiment with, and then thereby get more information. We have to go to large bodies in order to get any appreciable gravitational force.
Would you be using the planets as a sort of laboratory in space?
That's right.
What exactly more do you expect to find out about gravity by...
Well, we'd like to know how gravity arises.
You've no idea what actually causes it and how it operates?
Very little. I mean, we know something about the actual laws which it satisfies, but we don't know why it exists, how it arises.
Well, this is absolutely fascinating. You mean if you'd pick up a pencil and drop it on the table, you've no real reason as to why that happens?
We know that is really quite correct.
It's purely a phenomenon that you're familiar with and you can make rules about.
Yes, exactly. We know what will happen, but we don't know really why it happens, basically.
It's a staggering thing, isn't it?
No, it is a remarkable paradox, I think.
And a further paradox, I think, is that firmly though our scientists have their feet planted on the ground, they need space research techniques to understand what keeps them there. Next week, from this general survey of the subject, we'll be going into the details of how rockets work and how they're guided and controlled. Good night.
That recording of Looking into Space was introduced by John Stobbs. The other speakers were Professor Sir Harry Massey, FRS, E.C. Cornford of the Royal Aircraft Establishment, and M.O. Robbins, who is United Kingdom delegate to COSPAR.